Hello everyone. Today's lecture is all about the probability function, which is also referred to as the axioms of probability, which were introduced by Kolmogorov. And it is, although it was introduced long back, it is still very relevant in the probability theory study, which we study today. So, before I go into any technicalities, I would like to ask you a question. If I say there is a 200% chance of rain tomorrow, does it make sense to you? I'm sure most of you would say no. What does a 200% chance of rain mean? And if it means something, then how is it different from a 100% chance, right? There is no scale over here, if I may say it that way. And I can also not say that there's a minus 2% chance of rain tomorrow. That again doesn't make any sense. So, the very first axiom of probability, and you cannot think of it as axiom, you can also think of it as something obvious, right? Probability is never negative. At the bottom of everything, in all our studies of probability, we know that probability represents how likely something is, and negative likelihood really doesn't make any sense. For example, if I ask you, we have been studying the examples of tossing a coin or of rolling a die. In all of these, you can have zero certainty of an event happening, which is like an impossible event. Say, if I roll a die, I say, what is the probability of getting a 7? You can have a little certainty of an event happening. For example, what is the probability of getting a 1? Or you may have full certainty of an event happening. Like if I ask, what is the probability that you will get a number between 1 and 6? But you can never have a minus certainty. That doesn't make sense. So that is one concept just you should just keep in mind at this point that probability can never be negative. It won't make sense to keep a probability negative. Coming to the second thing which we should think about, the probability of a sample space of the sample space is 1. Now we have talked about sample spaces and random experiments in great depth, and you know that uh, if I have a random experiment and I tell you, ask you what the sample space is, it is a set of all possible outcomes, right? If I roll a die, in that case, my sample space would be this is my sample space, right? And this is also part of our sigma field, as we have defined the sigma field. The full set, that is the full sample space, as well as the empty set, is part of the sigma field, right? So this is, I can call this as an event as well, right? This is also an event, and this is an event of saying that I can get anything between 1, 2, 3, 4, 5, 6. Well, what is the probability of this? It is 1 because the sample space is defined in a way that it is a set of all possible outcomes of a given experiment. And if I ask what is the probability of getting any of all possible outcomes, then it is definitely 1 because if that is not the case, then you have defined the sample space in a wrong way, right? Okay. Coming to the third aspect, addition rule for mutually exclusive events. Now, we can go into the details of mutually exclusive events by an example. What if I ask you, what's the probability of getting a 1 or getting a 2 when you roll a die? Now, these events don't overlap in the sense that it's not possible that both of them happen at once. Now, suppose I make another set of two events. Say, event number one is I get either a 1, okay, or I get a 2. And event number 2 is I either get a 2 or I get a 3. Now, these events are not mutually exclusive. In what I mean by saying is that they overlap. And the overlap is what if I get a 2? In that case, both event 1 and event 2 is satisfied, right? So this basically means I get a 1 or a 2. This means I get a 2 or a 3. And if I get a 2, I am satisfying both the events. So in this case, I'm not talking about this case. I'm talking about cases where both the events are such that they cannot happen together. So, for example, I get event 1 is getting a 1 and event 2 is getting a 2, or event 1 is getting a 1 2, event 2 is getting a 3 4, right? And this is a very interesting way of we call this Venn diagram of showing such events. So let A and be two events. If they are mutually exclusive, it means that they don't overlap with each other. And if they are not mutually exclusive, it means that there are certain situations, like in this particular case, if you get a 2, that both of them happen. So in that, I'm not talking about that case. I'm talking about the case when the events are mutually exclusive. And if they are, then the probability, we if the events don't overlap, we simply combine their chances. So if I have a probability of event 1 and I have a probability of event 2, okay, then probability of event 1 union event 2, which basically means I get a 1 or a 2, is the probability of event 1 plus probability of event 2. And but this is only for the case where the events are mutually exclusive. They do not overlap. There cannot be any situation in which both the events occur at once. Occur at once, I mean that in one particular outcome, I satisfy the conditions of both the events, right? So this is the essence of the three conditions of the axioms of probability. Let me formally define it to you. And before I go into the formal definition, I want to share the essence that why it is needed. So, since this is a mathematical thing that we're doing, this is a mathematical thing, a way of measuring uncertainty or certainty, the study of probability. So we need certain rules, and these are actually very less rules. These are just three rules, honestly, and this defines the and this this keeps the probabilities in track for everything. So the all you need is for your probability to satisfy those three conditions, and you're good to go. So that's a big thing, and that actually simplifies a lot of your uh, problems. So we need rules that prevent nonsense. It's not that you define a negative probability, you define a 500% probability. Like you don't have any scale. Some person gives a 500% probability for the same event, and someone gives a 1000% probability. So in that case, there is no consistency. So to keep consistency and to allow calculations and allow calculations in such a way that everyone gets the same result, right? So these axioms make sure of that. If I want to formally define this, uh, I would like to start by giving a definition, which this is the definition I took from the book Casella and Burke. Name Statistical Inference. This is a really great book. You can also go through it. So, suppose I have a sample space S and a sigma field associated. So I have defined sigma field to you earlier, and sigma field, although even if we are defining finite sample spaces or we are talking about infinite, countable, uncountable sample spaces, we now know what the sigma field will be, right? And with every sample space, there is an associated sigma field that is actually the set of events where we can define the probabilities. All right. Uh, and that's why in this particular definition, the axioms are defined as a probability function. And you can see that it is a function with domain B. B is our sigma field. Domain B means that so each function has a domain and a range. Domain means what all it can take as input, and range means what will be the output. So any probability function has the domain of sigma field, and actually has a range of 0 to 1. It can be anything between 0 and 1. All right. So that is how the probability function is defined. And these are the three axioms which are defined in a mathematical way. The first one is that for all events in the sigma field B, so all the events that we wish to find the probability to, the probability is greater than 0. Second, the probability of the whole sample space is equal to 1. All right. And this actually limits our probability from 0 to 1, right? You cannot uh, you cannot have a probability more than one because the probability of the whole sample space is one. So that is the biggest event that there is, right? So that limits the probability function's range to be 0 to 1. And in the second one, what I mentioned earlier was uh, if we have mutually exclusive events, then we just the union of the probability of the union of those events is actually just the sum of those events, right? And this is actually applicable for countable set of events as well. So like if I say a1 a2 a3, all right, they are mutually exclusive, or pairwise disjoint also means the same. Pairwise disjoint actually makes sense for more than two events. So for more than two events, if I have every two events mutually exclusive, we called we call those set of events pairwise disjoint. So it's just a term. So like if I have a1, a2, a3, if a1, a2 are mutually exclusive, a2, A3 are mutually exclusive, A1, A3 are mutually exclusive. Then we called A1, A2, A3 pairwise disjoint. Okay. So, yeah, so that's what they're saying, that if they are mutually exclusive, which means that they're pairwise disjoint, then the union is equal to the sum. And I have defined it earlier in case of finite events, but even if I have infinite countable events, this still holds. All right. So these are the three things that you should ensure when you're defining a probability. And one thing I want to make sure that you understand here is that this definition does not tell you how you should define probability for a certain event. It just tells you that this has to be satisfied. Okay. Now, if I take the very easiest example of tossing a coin, right? What is the sample space? The sample space is head and tail. And what is the sigma field? It is phi, it is the null set, it is head, it is tail, and it is head tail, right? Now, suppose I say that probability of getting head is 1 by 5 and probability of getting tail is 4 by 5. Okay. And probability of getting head tail is by definition of this, it is just 1. All right. Now this satisfies all the conditions uh, of the axioms. So this is a valid probability function. But if I say that I have a fair coin, right? Now this with your own judgment, you can say that if it is a fair coin, then this should not be defined like this. This should be 1 by 2 and 1 by 2. But this nothing of this sort is mentioned in the axioms. This is also a valid probability function uh, based on our axiom. So what I want to say is that the axiom just tells you how you should define the probability function, but it does not tell you for a like you should have there should be some domain knowledge involved, and based on what kind of experiment is being held, you actually define the probability of that event. All right. Uh, so that is what I wanted to mention here. It does not give you a formula that, okay, this is how you calculate probability in any given situation. It just tells you rules that this has to be satisfied, whatever probability function you define. And but the probability function that you think of should be thought of carefully. given you know the full experiment being shown to you. That is when the probability that you calculate will make sense. So yeah, that's how I would like to end this lecture, and hope you guys enjoyed this lecture. I'll start giving more examples on this in the next lecture and try to make it more easy for you to understand. I hope this was clear, and let's meet in the next class. Thank you.